I'm Daniela Jones. I'm an assistant professor in the Biological and Agricultural Engineering Department at NC State. I also hold a joint appointment with Idaho National Lab, and at NC State, I'm the Data Science Academy Director of Agricultural Analytics. In this video, you will see a project that we did as part of a class that I teach, Advanced Analytics, which is part of the Agricultural Data Science Certificate here at NC State, and I hope you guys enjoy the project.
For years, we had been working on farms to try and develop a foundation for these farms to work within a soil component. As a soil scientist, it's always good to know a variety of things, such as the amount of clay that's in the soil, the soil color, the depth of the water table. All these things are very important for us to understand from a crop function. So when I heard about this new soil optics device, sensor, that you can mount onto an ATV, you can drive it across the field. You mount it on an ATV, you go to the field and you drive across. About every 6 feet, it will collect information regarding it's a passive sensor. It actually collects radiation, natural radiation coming from the soil. Soil optics can then convert that information over to what they call a count rate point, and that point will be a reference to the amount of clay, silt, and sand. So then what that allows us to do is have a very high resolution map, as opposed to possibly hand-augering every couple acres. You're getting soil information every 6 feet. This will allow us to more accurately predict things such as fertility loss, where to apply fertilizers, possibly yield estimations on sweet potatoes. And a lot of times this is very important for us during the growing season, so that we can make in-season management decisions and adjustments, perhaps, depending on the weather and how the crop is faring in the field. That we are collecting with the count rate, with the soil optics machine. We've also tried to integrate that information with other data that we have collected from combines, tractors, and sprayers, along with other soil fertility data and climate data, such as the NOAA weather stations. As we brought all that information in, we created a tabular data set that combined that information that you will see in the model, that helps us produce possibly an outcome that allows us to determine whether or not the soil optics machine is a valid way to go. Is it a higher accuracy? Is the trade-off for accuracy a better way to look at the information, or do we need to continue on with what we're accustomed to using, such as a hand auger?
In this case, we're using the build models section in the analytics lifecycle from the SAS VIA, which has been remarkably good at the collaborative experience between my team members. Actually get a good comparison between the models. At the end, we want to get a champion model that better predicts yield or count rate in this case.
I hope you guys enjoyed the analysis, that data integration, and the explanation of how we're trying to tackle this problem, this real-life problem with real data. The students have taken the first stab at applying machine learning algorithms through SAS VIA, and the class is not over yet, so we'll continue moving forward with a deeper understanding of our problem and hopefully make an impact on industry.